Hello, everyone. I'm Dael Amzalag. My project this summer was about hybridizing traditional and next-generation reservoir computing to accurately forecast complex dynamics. So, what is forecasting complex dynamics? Basically, the task is given some dynamical system and its past states, we want to be able to determine how it will evolve in the future. If we're able to do that, we have some interesting applications, such as predicting disease outbreaks, forecasting weather, or power grid dynamics. Generally, any dynamical system we want to be able to predict. How do we do that? Well, we have two main methods. The first, reservoir computing, is an established method which uses machine learning and specifically a reservoir. The reservoir, over here in the middle, is a randomly generated recurrent neural network that has very complex dynamics that we're able to tap into for our prediction. Basically, during training, we take data from our target system, U of t. It goes through the reservoir and transformed into our reservoir state vector. And then we train a weights matrix to match the reservoir state vector to our next step prediction. After training, the reservoir goes into autonomous prediction, where instead of using system data from the system, we use the reservoir's own predictions as the data in order to predict the next step. And so the reservoir is able to produce, or the reservoir computer is able to produce predictions over a long range of time. Our next scheme is next generation reservoir computing. It's based off of RC, but it's meant to have no neural network. Instead, we take multiple previous time steps of the system, and we construct some nonlinear combination of them, which is the representation vector O of t. In this case, we chose second-degree polynomials of our previous time steps, and then we train a weights matrix to predict our next step. NGRC seems to be pretty promising because it often performs very well, and when it does so very efficiently. It doesn't need much training data, and it doesn't need much computation. But both RC and NGRC do have some weaknesses. NGRC tends to be very unstable, which means that it might randomly go up to infinity and stop predicting altogether. And it also really, really depends on the type of nonlinearities you choose. And then RC needs a lot of training data comparatively, and it needs a lot of optimization in the hyperparameters, like the size of the reservoir, the connectivity between the neurons, and other things. So what do we do? Our approach was to make a hybrid of the two. Basically, how the hybrid works is we take data from the system and transform it both by the NGRC transformation into O and the reservoir transformation into the reservoir state R. We then combine both of them into a hybrid vector H and train a weights matrix on that. And then we do autonomous prediction after training. There are two main reasons we think a hybrid model might work. The first, previous attempts at hybridizing RC and knowledge-based models have shown greatly increased performance. The main principle behind that is that the two components of the hybrids contain different information. And even though both individually might not do well, if you combine the information, you might be able to get good predictions. We speculate that RC and NGRC will work in the same way, both containing different information. And in that case, because NGRC is so efficient, we have a low-cost addition to RCs in order to greatly improve performance. The other reason we're looking into this is we hope that we'll be able to fix the weaknesses of RC and NGRC individually by combining them. Our hope is that a hybrid might be able to address the brittleness of NGRC, but also decrease training time that is required for RC. But how do we evaluate how good a scheme is? Well, we have two main measures. The first, valid prediction time, or VPT, basically means the amount of time where our prediction matches up with the true system we're trying to predict. The second, climate, concerns more after the valid prediction time is over, where we try to see in the long term, does our prediction match the look of the system we're trying to predict? One example system that really showcases the power of our hybrid model is Mackey-Glass. Mackey-Glass is a delay differential equation that exhibits chaotic behavior, which means it's very difficult to predict. The equation is over here. On the left, I have a graph of the dynamics of both the prediction in blue and the true dynamics in red. Horizontal axis is the amount of time steps, where each time step is 0.01 seconds. Vertical axis is the system value. At the top, we have RC, which you can see can predict decently well, but then goes off into this periodic state. NGRC, which does worse and is basically periodic for the entire time. And then the hybrid, whose prediction is classified by this little black line, does much better. And if you might notice, it also manages to sort of recreate the look of the system even after the valid prediction time is over. For a bit more statistics, I also ran this test on 1,000 different iterations with different initial conditions, and I made a distribution of the valid prediction times. We have RC on the left, NGRC in the middle, hybrid on the right. The lines here indicate the mean valid prediction time. And as you can see, on average, the hybrid model improves on both models very, very well. Again, I'd like to note how the hybrid manages to recreate the system's feel even after the valid prediction is over. And I tried to measure this a little more accurately with the climate in two different ways. First, on the bottom left, we have a graph of the hybrid prediction and the true system power spectrum, where a power spectrum basically shows how much each different frequency contributes to the system. If two different power spectra match, it means that the two systems are very close to each other. And as you can see, hybrid in blue, true system in red, the two are very, very, very close, which indicates that they do actually recreate climate very well. The other method we have to measure climate is with attractor reconstruction. In this case, I'm graphing the prediction trajectory in time delay space, which means I'm graphing the current prediction versus prediction 2 seconds ago versus prediction 4 seconds ago. And what we're looking for is the general shape of what we call the attractor. So as you can see in red, we have the true attractor, this little squiggly thing. And on the bottom, NGRC and RC completely fail to recreate that shape. They do something completely different. Yet, the hybrid, combining both of them, manages to do a pretty good job in recreating the climate. So, for conclusion, we see that an NGRC-RC hybrid manages to improve performance quite a lot for many different systems. On some systems, usually when both the RC and NGRC perform either very badly or very well, the improvement is more modest. So for our future steps, we want to test more systems. Some of them are compiled in reference 4. The others are experimental data, such as weather forecasts or sunspot data, in order to classify when a hybrid model works well. These are my references. I'd like to thank Dr. Serrano, the coordinator of this program, for making this possible and helping me quite a lot along the way. Thank you.